So far, you have learned about pipe head loss, which can be calculated using Darcy-Weisbach equation, and you know how to calculate F for laminar flow and for turbulent flow now. So now that we learned about pipe head loss, which is as a result of friction and turbulence, we're going to focus on component head loss. Component head loss or minor head loss is associated with flow through devices or fixtures such as valves, bends, and teeth, because when flow moves through these fixtures, it loses some energy. It loses some mechanical energy. So it is important to be able to calculate this kind of head loss as well. To do that, engineers use a coefficient K called minor loss coefficient. So minor loss coefficient or K is simply the fraction of piezometric pressure drop over kinetic pressure. So if I want to write this fraction using mathematical notations, you know that piezometric pressure is P sub Z, and pressure drop is delta P sub Z, and kinetic pressure is basically the pressure as a result of your velocity that can be found using stagnation tube, and it is rho velocity to the power 2 divided by 2. Perfect. So now remember that in previous session, the start of previous session, I showed you that this term, which is the piezometric pressure drop, is what is your gamma of fluid times HL head loss, right? Now, and our goal is to find head loss, minor head loss, right? So if I rearrange this equation and write it in terms of head loss, then I can write that gamma HL is equal to K times rho times velocity to the power 2 divided by 2. And I know that gamma is equal to rho times G, right? So this rho cancels with this rho, and G can go to the denominator of the right-hand side of the equation. So HL, or minor head loss, or component head loss, is equal to K velocity to the power 2 divided by 2G. Now, it is important to note that this K that you have in this equation is your minor loss coefficient. So this is minor loss coefficient. Depending on what kind of fixtures you have, the value for K is going to be different. So if you have a T, the value for K is something. If you have a gate valve, it's something else. If you have a filter, it's something else. If you have an elbow, it's something else. Now, we are going to find out how to find these values for different fixtures in a pipe and how to calculate the value of minor head loss. And then we'll add that value to our equation. So the summation of pipe head loss and your component head loss for your system is going to be your total head loss, or HL, for every system that you are working with. These are some general rules that you should remember as an engineer. So K, the value of K, and what is K again? So in the minor head loss, we have a K times velocity head in the pipe. This K is larger when pipes extend than when they contract. So I think I've told you before that when you have a contraction like this, you have a separation region that I'm going over with my green marker. This is the separation region, and this is the separation region. this separation region creates some energy loss, head loss, right? But because this is a contraction, this separation region is smaller, so your head loss is smaller. Now, if you have something that from a pipe flow goes through a tank, this is expansion, right? The separation region that the expansion creates over here is way larger. So the energy dissipation will be larger too, okay? The other thing that you need to consider is that K is larger when changes are abrupt. Again, I have introduced you to this before a little bit too, rather than gradual. Okay, now also K, we have K from change in the direction. So if you have basically a pipe that curves like this, again, you will have some separation zone, separation region over here, which results in loss of energy, and we need to consider that. And finally, how do we find K values? The good news is that lots of people over the course of decades have done many experiments on different pipes with different diameters, different curvatures, and they have tabulated their results for us to use as engineers. Okay, I have two videos for you on this slide. One video is related to a globe valve, and the other one is related to a gate valve. The reason that I'm providing these two videos for you because I wanted you to know the process that these two different valves modify the course of flow, the course of water in the pipe system. As you can see, whenever flow is going in this direction, then flow goes up, and then in this direction. So the course of flow significantly changes in a globe valve, right? In other words, the flow loses a lot of mechanical energy because of this movement. However, take a look at the gate valve. Whenever flow is going in this direction, the flow some part of the flow goes up, but the flow mostly continues going in this direction. So although there is some energy that is being dissipated in gate valve as well, the course of the flow doesn't significantly change, right? Because of that, usually the K, or minor head loss coefficient for globe valve, is usually higher than K, or minor head loss coefficient for gate valve. So this is true for all other valves, or for all different types of transition and fittings and fixtures as well. So I want you, whenever I'm talking about this in K values for different fixtures, in your mind, think about how flow is going to change its course, how bubbles are going to be introduced into the flow that represents energy dissipation, and then realize why this K, for example, for this fixture is larger than that fixture. All right, so now I'm going to show you how to find minor loss coefficient, or K. This table that I have provided a picture for you over here is table 10.5 from your textbook. So whenever in a question you have a pipe fitting or a bent or a valve, whatever, in your pipe system, you need to go through this table, which has been developed by using many experiments in the laboratory to develop the K values for different type of problems. For example, so under description, you can see that we have pipe entrance, there are contractions, expansions, 90 degrees bends with vanes, and vanes are very small metal plates inside the pipe to basically direct the flow, and this is the smooth bend and or different fittings that you can have, like globe valve and angle valve, gate valve, so on and so forth. All right, so Let's take an example. This example, we are going to find K sub E for sharp-edged entrance into a pipe. What do I mean by that? So sharp-edged entrance means that if your pipe looks like this, so you have water over here, and water goes through this pipe, and these are sharp edge entrance. So some energy is going to be dissipated because of these sharp-edged entrance over here and the vortices that are created over here, right? So we are going to find the minor loss coefficient for this scenario for sharp-edged entrance. First, you need to find the entrance, and you can see that over here we have pipe entrance and the equation for pipe entrance, and K sub E is the minor loss coefficient. Now, then, under additional data, you need to find R over D of your desired condition. R is the radius of the curvature over here, and D is the diameter of the pipe downstream. So because in our example, we are looking for sharp edged, there is no diameter, right? So R is 0. When R is 0, then R over D is 0. So I am looking for this condition over here. So I'm going to find K sub E for that condition, which is 0.5. So for this condition, K sub E is 0.5, and head loss, minor head loss, because of this sharp-edged entrance to a pipe is equal to 0.5 velocity to the power 2 divided by 2g. Okay, so now remember, from now on, even if I don't tell you in a problem statement that there is going to be some minor losses because of the sharp-edged entrance from a reservoir to a pipe, you still need to consider this equation. This equation from now on should be in your knowledge. So even if I don't mention it in the problem statement, if you have a sharp-edged entrance, you need to memorize and know this equation and incorporate it to calculate total head loss. Now, let's take a look at another example. So here, it was 0.5. Now, the other example says, what is K sub E, but this time capital E, for a sudden expansion into a tank? Okay, so we have had that kind of experience before as well. There's a pipe with diameter D that goes into a tank like this, a tank of water. The flow is in this direction. Obviously, as flow goes through this, there's going to be some vortices over there, and there will be head loss. So what we are going to find is K sub E for this kind of expansion. First of all, you need to find expansion. It's over here. Then you need to find the situation that applies to your problem. We need to calculate D1 over D2. We need to calculate this. What is D1? D1 is diameter of the pipe that you have. Okay, so this is the diameter of the pipe that we have, D1. And then D2 is the diameter of the pipe after pipe 1. So in our case, because this is going into a tank, and the tank, what's the diameter of the tank? It doesn't have a diameter, right? It's very, very large, right? So D2 would be infinity. It's because it's very, very large, infinity, right? So a number divided by infinity would be 0. So we are looking for this condition. Now, next we need to find theta. Is theta 20 degrees or 180 degrees? It's pretty easy to find out. How? So theta is this angle, the angle from this wall to this wall. And obviously this theta over here is 180, right? So we need to select this one. And for 0, for D1 over D2 of 0, 180 degree, the value of K would be this value, which is equal to 1. So HL, or minor head loss, would be equal to 1 times velocity to the power 2 divided by 2g. You should be familiar with this equation before. Remember that I showed you for these kind of expansion from pipe to a tank, this is the equation that you use to calculate head loss. You should be familiar with this from our lecture before. And eventually, what I want to tell you is that no matter what you have, you could have a bend, you could have a globe valve, you could have a T, you could have a 90 degrees elbow. You need to go and find the K and put it into the equation that you know, K times velocity squared divided by 2g, to calculate minor head loss. One question that you might ask is, what if I have multiple pipes and multiple pipe fittings? So, for example, there is one pipe over here, another over here, one over here, one over here. And then there is an elbow over here, there's a valve, there's another type of valve over here. So there will be multiple head losses. How do I approach these kind of problems? It's pretty easy. So your total head loss, or HL, would be equal to summation of head loss or pipe losses from all different pipes. So Darcy-Weisbach equation for pipe head losses for all different pipes, plus summation of head loss as a result, or minor head losses, or head loss as a result of components for all different components, would be your total head loss. So the answer to the question is, if you have multiple fittings, multiple pipes, use the summation of those to calculate your total head loss in the system. Now we're going to take a look at one example that is a combined example. So you have both pipe head losses and minor head losses. If oil with given kinematic viscosity and given specific gravity flows from the upper to the lower reservoir, exactly like the picture, like the photo that you can see on your slide, at rate of 0.028 cubic meters per second, that's our flow rate, in the 15 centimeter smooth pipe, and it is important to note that it is a smooth pipe, then what is the elevation of the oil surface in the upper reservoir? Perfect. So we want to find the elevation, meaning that Z1 is the thing that we want to find. We need to write, obviously, energy equation between sections 1 and 2 on this photo. But in order to do that, first we are going to calculate velocity. Just to save some time, I have already calculated velocity for you over here. And then I use that velocity to calculate Reynolds number, and just to show you that Reynolds number is greater than 3000, which means that our flow is turbulent, and alpha, which is the velocity correction factor, is equal to 1 because it's a turbulent flow. Then I wrote energy equation for sections 1 and 2. Obviously, we don't have any pump, we don't have any turbines, so those are 0. And pressure and velocity on the surface of the two tanks, left-hand side and right-hand side, those are all 0. So we end up having this equation. In order to solve that equation, we do have the value of Z2, elevation is 130 meters. So we have Z2, we need to calculate HL to be able to find Z1, right? I have written the general equation for HL, head loss, total head loss. Total head loss is the summation of pipe head losses and component head losses. Now, the question is, how many pipe do we have? So usually when the diameter changes, we have different pipes. But in this example, all along this system, from here that I'm going over, from here all the way to the other tank, we only have one pipe. How do I know that it's one pipe? Because the diameter doesn't change. The diameter stays the same thing. So we have the total of one pipe. One pipe. So we need to find F based on that diameter. Now, how about the components though? How many components do we have? Let's take a look. we have an entrance over here. So we need to find the minor loss coefficient for the entrance. We have two bends, one over here and one over here. But both bends have radius divided by diameter of the two. So we'll find K sub B and K sub B. These two K sub B's are equal because radius divided by diameter is equal to 2. And finally, we have one exit or expansion, K sub capital E. Okay, so we have 4 different components, right? One entrance, 2 bends, and 1 expansion or exit, right? So I'm going to write the equation for HL once again. HL is equal to F L D velocity in the pipe to the power 2 divided by 2g. That takes care of the pipe head loss, plus for the component head loss, I'm going to go one by one. We have one entrance, so it would be K sub E velocity to the power 2 divided by 2g. I have 2 exact same bends. How do I know that they're exactly the same? Because R divided by capital D is the same. So it would be plus 2 times K sub B velocity to the power 2 divided by 2g plus one exit or one expansion. It would be K sub E times velocity in the pipe to the power 2 divided by 2g. So this is my total head loss. Pipe head loss plus component head loss. Now, we need to find K sub E, K sub B, and K sub E capital. And these are the values that you can find from table 10.5 that I just showed you. So if you go to table 10.5, you can see, and I'm going to write them over here, but I want you to go to the table and see if you can get the same numbers. So K sub E, small e, which is entrance, I want you to memorize this. This is always 0.5 for squared edge or sharp edged entrance. For sharp edged entrance, it's always 0.5. Then KB, having R over D of equal to 2, would be equal to 0.19. And then K sub capital E would be equal to 1, again for sharp edged exit or expansion. These are the values that you will get from table 10.5. All right, so you can see that there is velocity squared divided by 2g in all of these terms. So I'm going to take it out of the brackets and write the equation for HL as velocity of the pipe. All right, and then it would be F L D plus KE plus 2 KB plus K sub capital E. All right, so I have these values based on the table. I have the length of the pipe. I do have the diameter of the pipe. I do have the velocity and G. The only thing that I need to find is F that I need to find from Moody, having the value of Reynolds number, and K sub S over D. You might ask, we do not have the value of K sub S over D. Yes, we do, because remember that we know that this is going to be a smooth pipe. So for a smooth pipe, there is a specific line. Now, in the next slide, I'm going to go to Moody diagram and show you how to find F value. Finding F friction factor is pretty easy because we have Reynolds number 5.93 times 10 to the power 3. 5.93 is almost 6. So first I'm going to find 10 to the power 3, and then the value of 6 or 5.93 would be somewhere over here. And remember that the pipe is smooth, so we are going to use the smooth pipeline, which is the last curve in Moody diagram. So what I'm going to do is to continue over this line, this vertical line, until it intersects with this line over here, and then go through the left hand side over here, and then my line is not pretty straight, but I'm gonna accept it. So F, based on this, I'm gonna say it is 0.03, is it 6? Yes, 6. All right, so this is gonna be the F that I'm going to use in the equation that I developed in previous slide. I'll show it to you in next slide. Now we have everything. We just need to plug in all the numbers into the HL equation, and I'm going to do that. So it would be 1.58 meters per second to the power 2. F from Moody is 0.036. L is 60 plus 7 plus 130. It would be 197 meters. Diameter is 0.15 meters plus 2 times 0.19. And again, K's are all from table 10.5. And if you calculate this value, it would be equal to 6.25 meters. Now, Z1, elevation of the surface of tank 1, is going to be Z2, which is 130 meters given to us, plus 6.25 meters. It would be 136.25 meters. And this is the answer for the elevation of tank 1.